Okay, the recording is started. Today we are going to discuss Monte Carlo simulations in Kotlin. In particular, how it is done from inside, how the Monte Carlo engine works, and also we would like to discuss two particular simulations, one about neutrino physics and one about atmospheric physics, but both are, of course, about electrons. First of all, a bit of theory. Let me share the screen. Maybe I just should share the entire screen. Yes. Yes. Okay. Now a little bit of theory about Monte Carlo simulations and some problems we encounter with the Monte Carlo simulations. First of all, what is the essence of the Monte Carlo simulation? At least in physics, of course, we have a broad range of different applications of Monte Carlo, but usually we just use a random number generator or to generate some kind of event. It could be different. It could be economical simulations, it could be biological simulations or physical simulations. If necessary, we are using the result of this event to generate the next event. For example, in physics, we have particles. We have interactions of some kind of particles. For example, electron hits an atom and produces another electron or a photon. And then we use this photon or electron to simulate the next stage of next particles. An important part which physicists tend to forget about is the processing of the result, because you need not only to simulate the next particle, but also somehow use the information you got from the previous simulation. For example, you have to dump it to the hard drive or display the plot or process it in any other way, but it also have to be taken into account. And then we can start the simulation again and process the next event. Basically, we see this kind of picture, like we are generating, then processing, then generating, then processing. And we are doing it sequentially, and it is quite easy. We always use all the resources we have, at least in one processor core, because we start processing as soon as we finish generating an event, and we do not start generating next event unless we finished processing. It's okay, it is working, but the problem, of course, is it is sequential. So you can't utilize modern parallel processing environments for that. The only way you can is to start multiple such generating processing chains in parallel, which people usually do with a Giant or something like that. Of course, it also means that different generations do not depend on each other. This means that you can start generating events for the same simulation, because you probably will need the result of one generation to affect another generation. In parallel, we would like to see it like this, like we are generating some bunches of events in parallel on different cores, on even in different systems, and then processing them together. The processing should be done together because, as I already said, you usually want to use, you have to wait for all processes to finish, because you usually want to merge their results somehow, and either affect the new generation here, or you want to dump the results here and wait for all processes to finish and finish this bunch of simulation and then start another simulation. It's the ideal case, how it should look like in the mental picture, but actually it does not. Usually it looks like this. So different simulation branches take different time. And so you have to spend your computation resources in a not very effective way. In best situation, you have some kind of dispatcher which can start some small processes here when this generation is finished. But in general, you just have to wait until all simulations are finished in order to continue. There is no way around it as long as you are doing this blocking here and waiting for the result processing. For example, if you want to dump all the results of the simulation into the same file, you can't write data in parallel to different parts of the file because it will bring a lot of errors and will just break the process. So you have to do it that way. How to solve this problem? The possible solution to this problem is the asynchronous processing. This is actually done in all IT industry right now. Nobody do blocking operations because they are too expensive. So people are doing asynchronous calls like this. You do not think about the processing. You have some kind of callback, which means when you start generation, you pass the function which will be called when the generation is done to this generator. And when it is finished, it will send some kind of event to specific software which will do the processing. It's quite convenient, and you can also have some kind of software which collects all the results of those callbacks and, for example, write it to the database or to the hard drive in asynchronous way without thinking about what is the order of completion of these events. Of course, there are some limitations for this scheme as well, because you need to, if you want custom processing, you need to set this processing ahead of time. Because it's a fire and forget scheme, you cannot use the processed data to affect new generation. So it has some limitations, and of course, you do not see any parallelization in the scheme. You need to do it externally and watch for possible data races, to possible parallel I/O, input-output problems, etc. But in general, this is way to go. Now, what different ways are there to do this asynchronously? You can do it in the push way, like it is shown here. The push way means that you start some number of events simultaneously, and then they are dispatched to the number of cores you have, and you wait for them to be processed. Each event, when it is finished, it sends this asynchronous callback, and the simulations is finished when all events are processed. Of course, if there are some mistakes, there are some problems, like in C++, you have a segmentation fault inside one process, it will break anything. And if it is not a segmentation fault, you will have some kind of a way, you have to have some kind of way to recover from this error and write appropriate login data. But the main problem is that if you want, for example, to add some kind of custom processing here, if you want to some kind of multi-stage processing here, you need to make this advanced callback, which takes into account all those things you want to do with the data and use it ahead of time. Another scheme, which is made possible with the modern technologies like reactive streams, is a pool model for Monte Carlo simulation, which means you have a lazy event flow. What does lazy mean? Lazy means that you do not compute anything. You just create a function that will compute the event when it is requested. Then I will show it today. You can use reactive stream composition to not only to process these events, but also to compose this processing from the ready build blocks. No need to create a custom callback each time, but you can compose it from pre-built processing pipelines. And what is quite important for us, you pull new event as soon as you are ready to process it. You do not need to think about different times it requires to finish process. It is possible, for example, that the processing takes much more time than the actual generation. Then, in this case, you are generating a lot of events here, and the processing takes a lot of time, and then this the time comes, then you just can't process all those callbacks. You do not have processing power to process them in the rate they are coming, and you need some mechanism for a so-called back pressure. What is important about reactive streams is that they have inbuilt back pressure mechanism, and we do not have to think about it. And we can process as many events, as large statistics as we want at each given time. We do not need to plan ahead our time. Say we plan to take millions of events and we do not know what time will it take. We can say we will process events for an hour and not more. It's possible to do because you can customize the conditions of pooling dynamically. It's almost the end of the theoretical part, and we will come to the code and to discussing the code. But I want to make an announcement for people who will hear it in the recording that we are currently working on the next stage of such framework. We are working on the Simba project. It's not about Lions. It's about simulations with the Bison tools. And the idea is to use coroutines, asynchronous streams and coroutines, to implement a fully parallel asynchronous event generation. It includes a little bit more complicated and sophisticated mechanism which I call random branching process, because here we have one event generating one event, but in particle physics, usually you have one event generating a random number of events. So it's a little bit more complicated. What is important thing that we will use Bayesian probability propagation to limit the number of computations we need to do in order to get the result. I won't get into details right now, maybe later. And other technical tools like, for example, deterministic random seed propagation, which is very hard to do in the parallel threaded environment, but it is possible to do in coroutines. And in distant future, we are also want to asynchronously call event generation on the remote simulation, remote computing nodes, which is also possible when you fully embrace asynchronous way of thinking and asynchronous way of doing things. Okay, that's for a theoretical part. And if there are any questions right now, you are welcome to ask them. You can ask in Russian. I will translate on flight if you want. Okay, no questions. Let's get to the next stage. It's the actual code. And we today have two tasks, two problems I want to show. It's both of them as old code. A few years I wrote a few years ago, but they will show problems. First of all, it's trapping. It's there is experiment called Troitsky mass, and there is a magnetic source in this experiment, which is actually just a pipe, pumped down pipe with different magnetic fields. In the center, you have a smaller magnetic field, and then you have those transport magnetic fields, which are larger, 3.6 Tesla. And on one end, you have a strong magnetic field, 7 Tesla, which is called a pinch magnet. And what happens with those electrons? Here on this side, we have a detector, a spectrometer, and detector of the Troitsky mass experiment. On this side, we have a so-called rear wall. And we actually count only electrons which pass here through this magnet. And all electrons which are going here are dead. They do not ever return from the rear wall. And there is an effect called magnetic mirroring. It means that when the angle at which between the electron direction and the magnetic field line is large enough, it is reflected. It means that if the initial angle here is small, the electron will pass here and go to the spectrometer. But if the initial angle is large, it will be reflected either from this transport magnet or from this pinch magnet. And if the angle large enough, then it will be stored, it will be trapped in the source and going there and back again a lot of times. It's mean path of like 100 kilometers when the source size is about 3 meters. So it's a lot of times here. But there is a residual gas in the spectrum, in the source, and electron is interacting with this gas, and it changes during this interaction. It changes its angle and goes either to the spectrometer or back into the rear wall. And this is what we need to simulate. Okay, let's see the code. This one. I'll close everything. Probably I will have to switch into where it is, presentation mode. Okay. Let's see, the whole simulation is rather small. It's only several files here. And let's see it from the entry point. So please ask questions about Kotlin or things you do not understand. The entry point is rather simple. We have a main file. Next, we have a number of initial energies for electrons here, and some utility functions to compute the time of simulation. Kotlin allows it actually to do it in a more concise way. We just can do it right now. Okay, I won't change anything, but in Kotlin, you have a function time minutes, which will execute the block inside and return the time of the execution. Now, it's not quite a beautiful way to do these things, but here we have we are creating the simulation manager, then applying some kind of options of configuration to it, and then run a million events. Here it looks like we are using this. Here we are using this push model. Let's see it in the site. First of all, let's see the simulation manager itself. It has a file where we should store the output names and some processing rules. For example, we want here we have a generation rule, which No, it's not a generation rule. It's a rule to create a random number generator. And here we have a processing rule which evaluates each the result of each event simulation, and then chooses either to accept it or to do something else. You see that there are different stage. Oh, sorry. It selects events to be reported, to be put into the file, depending on this result on the simulation. Next, we have some configuration done here, and even magnetic field, which could be set as in the source, which could be set as a function. And now let's see, going back and see what does the simulate all actually do. It just repeats one process of simulation a lot of times. Let's see how it does it. The simulator is the object which actually does the simulation, which stores this simulation logic. And it takes parameters which we set in this our configuration object, and then we do this thing. Oops, sorry. The actual simulation is done here. Let's see how it is done. It's a push model. We are taking a range from 1 to num, which is the number of electrons we want to simulate. Then we transforming it using Java Stream API to a parallel stream. And then for each number, taking it as a parameter, we use I don't remember what this does. Okay, it just generates new random number generator. We create a generator, and we generate initial electron with a given angle and given position into the source. Both numbers are random. Kotlin asks me to remove math qualifier. So we generate random angle and we generate random position. And then we just run this simulation with a given initial angle, initial energy, initial position, random number generation, event identification, and when it is finished, we also increase the counter in order to get the statistics of the simulation online, not after it is done, or all events are done, but we are counting them just as they go. It's this callback or fire and forget, which I showed you earlier. Then we take from those events, we take only those events who correspond to this report filter. And for each of those events, we use a callback and push this event to the output. Here, actually, I do not, the Java Stream API works in a way that here I do not actually wait for all events to be computed before doing filtering. Those map and filter operation are fused together. It means that you will immediately both process the event and do filter and then do this operation on each event without without waiting for all of them to finish. In order to show you how you can change this composition, we can, for example, move this counter increasing to another stage, like oops. We can do it this way, map, and then we are doing its event, and then returning event from this lambda function and remove it here. It will be more clean. There you are. So now I am just adding a new block, and if you want to add some kind of custom logic here, all you need is to insert a block here without changing the logic of the simulation. Mainly, this is all what is to see in this simulation. Maybe we can discuss code in a little bit more detail, but I'm not sure it works worth the effort. For example, we can see how this simulate actually works, but it's just a straightforward function which takes the parameters. Then in the cycle, it generates the free path of the electron, and depending on this propagate, which is also actually moves the electron from initial position and with the given free path, it computes the either completes the simulation if it is in the finished position, or moves to the next step. It's quite straightforward. So what we can do right now is to run it. We're going here, and we will limit the number of simulations. Now it's a million events, and we will limit it to 100,000. For comparison, the same simulations done in like Giant or ANSYS, it takes about several days to finish. And here, since it's very simple, we are doing it very fast, and when it's completed, we can look into the output files, which are placed here. And here they are. You can see here initial parameters as comments, and then the table of accepted events. Since I specifically asked here, where it is? Here I specifically asked to accept only events with the accepted state in order to limit the size of the file. So we have all those events with their IDs. IDs are important. If you do not have a fixed seed, IDs are meaningless because each have its own random generator. But if the initial seed of your generator is fixed, then each ID will be bound to specific chain of interactions, and it will be fixed. The result will be bound to this ID. And additionally, we have here the output of this counter, which we were running in parallel. And here we have a number of events of different groups. For example, we now see that the number of accepted electrons is only 4,000 out of 100,000, rather small number. And then we have even less events which pass right through the pinch magnet on the initial step. And then we have a lot of events which go back to the rear wall, and even more events which are losing energy below the given energy threshold, which is 8,000 electron volts. That's basically all for this simulation. if you have some questions about it, please ask it right now. And if not, we will be moving to the next example. Okay, no questions here. Then we are moving to the next example, which is...
Sorry, Alec.
Oh, okay.
Sorry, I just thought about... So can you explain, please, again, how back pressure is handled?
Here, in this example, we do not have back pressure.
But
because
in general, how do you think
I will show it in the next example, how it is handled in Kotlin, because in Kotlin flows, we do it automatically. In general, back pressure is a special callback, which you pass some kind of callback, which you pass to your processing stream, and then when the processing feels that it is clogged, it can't take anymore, then it passes the event back, which says that please stop sending me new events because I have to work with those I have right now.
So there is like some kind of buffer, right? So
yes.
For example, I know, for example, Aka stream. This is an example of back pressure.
Yeah, yes. They have a back pressure. In Kotlin, it is much more simple. I will show it right now because this simulation we've done right now, it uses Java Stream API. It's not actually a reactive stream. It's more like more beautiful way of doing push model. But I will show you the pull model right now because in Thunderstorm simulation, the reactor-like model, we actually use a pull model. Let's see it. Yeah, here we are. Probably. Here we are. And this also, the model here is very small. It's several files, like 2 or 3 meaningful files. Oh, no, it's 2 files for a model, 3 files for some infrastructure, and 1 file I'm showing you here. It's a demo simulation because Mikhail did a command line interface here, which actually takes the parameter from the command line. And for this test, I want to show you how to work with a simulation from the idea. It's quite convenient, actually. Now, let's see how it looks like. Again, I'm taking custom random number generator because you always have to be safe with your random number generators, and I'm choosing specific seed just in case. Then I'm putting the parameters of my I forgot to state the problem. Let's see it here. The reactor model is the model of propagation of electron avalanches in the atmosphere. The thing is that if you have a strong electric fields in atmosphere, like 100 or 200 kilo electron volts per meter, which is a normal electric field in thunderstorms, you have accelerations of electrons, and we now know that there is events like terrestrial gamma enhancement. Yegor can tell us a lot about them next time, when we have additional X-ray radiation from the atmosphere. It's a registered fact. It's a lot of people around the world are studying those events, and we also have things called terrestrial gamma flashes, where you have extreme intense X-ray radiation from the thunderstorms, and there are still no clean explanation how those gamma flashes work. Very short, very extreme X-ray radiation. We do not know how they work, but we have some models. For example, our model, the so-called reactor-like model, assumes that there are random directions of fields in the atmosphere, and there are smallish acceleration cells, like few hundred meters, 100 or 200 meters. In each cell, we have an electron accelerating and producing gamma particles. Here you see those wavy lines as a gamma, about several mega electron volts. And then those gamma ignite, produce electrons, high energy electrons, in different parts of the cloud. And those electrons start to accelerate, and this process repeats just like the atomic reactor works. But instead of atoms, we here have chunks of the cloud with the size of several 100 meters. It actually works in the model, and we have a reason to believe that this model could be a correct description of the terrestrial gamma flashes. But it's too preliminary to state this, but there is some indication. So here we have not one particle propagating through the tritium source, but in fact, one particle produces several particles. So it's a little bit more complicated from the engine point of view. Now we are getting back here. So here we have some parameters of our atmosphere. Right now, they are just hard-coded in this example, but we can change them later. It's a local multiplication factor for about how many photons one electron in a cell produces, the photon mean free path, before it creates the electron. By the way, we forgot to discuss it in our recent seminar, that photon also needs time to produce electrons. The cell length, the effective size of this acceleration cell, the total size of the cloud, magnetic field is ignored right now in this simulation. It does not do anything. And here I also have additional parameter called a number of initial particles. We can start with one particle, but in order to get more reproducible result, we can start with several particles. And here we are creating this atmosphere model. Here it's a simple atmosphere, which means that it does not include any specific tweaks from the atmospheric simulations. It just creates a random fields. And what is important here is that we do not say how many events we want to generate, because we do not know it in advance. And actually, if there is a terrestrial gamma flash, the number of events is infinite, because each event infinitely is multiplied, and we don't know. It will never finish in this model. It will just increase and increase. So we are limiting the total number of produced electrons. We are finishing our simulation when it will, when the number of electrons will exceed this number. Then we create the initial particles. Here it's not very interesting. We're just creating 100 photons in the center of this cloud, with a direction downwards. That is altitude, and it's in the middle of the cloud. Yes, and the direction is downwards. Yes, as I said, and the energy is not critical right now. It's some. I will talk about it a little bit later. It's for visualization. And then the whole simulation looks like this. This is the whole simulation controls. Let's see how it works. Let's see how generate function works. The generate function is an extension function on the atmosphere. I decided to do it this way. This could be different design, but it looks nice. Which takes, it's not a member of the atmosphere class. It is done. It added it to it later, and it takes the random number generator and the initial number of initial seed particles, and then it produces an object called flow. Flow in Kotlin is the actual implementation of a reactive stream approach. So the flow is, in this case, it's a lazy stream of events which we can pull from later. In order to create this, we are just using this function flow, and the lambda inside this flow we have this so-called flow collector context, and when we call it, it has emit function. Emit function, we can look into it. It's just one single function of the flow collector interface. So what we are doing here in the infinite cycle, or in this case, not an infinite, but we are checking that we have some particles, because this avalanche could die out. If we still have particles, then we generate a new generation. On the first step, it's just initial seed generation. On the next step, we emit current generation and then use current generation to produce the next generation. In this case, we are not propagating, we are not doing it completely asynchronously, but what we want is to, on each step, produce all electrons or photons which are produced in this generation, and then compare them. It is convenient right now. It could be done fully asynchronously, but we do not need this in this case. Let's see how this next generation works. Here we have actual simulation logic. It's a familiar thing. It's a Java stream parallel processing. I mean that all electrons in one generation are processed in parallel automatically. And what we do is to compute the interaction points of the photons and electrons, and then propagating them through this cell acceleration. I think I won't go into detail here. And then when this processing is finished, we just collecting those particles into a list. And we returning a list of collected particles, both electrons and photons. So how does it work? What Roland asked, how does it work? You see this emit function is marked as suspend. Here we can see it's a suspend modifier here. It means that when we are taking new event from the flow, we are running from this cycle, and it is emitted, and we are running forward, and then we come here again and come again to emit function. But if we finished this cycle here, and our consumer, which consumes the flow, did not take the event, then at this point the program is suspended. It means that it will just seize all resources, all computing resources, and wait until the consumer actually takes this event. When it happens, it will unsuspend automatically and move forward and do another cycle. This is actually a form of back pressure, because this suspension is an internal feature of the Kotlin, and actually this async await is implemented. The coroutines are implemented in most of the modern languages, but with a different level of convenience. In Kotlin, it is quite convenient. You do not need to think at all about it. This back pressure in terms of yielding the resources is applied automatically. Now, let's go back and see how as you can see, the number of generation is infinite. We are not limiting. We are not finishing the process here unless the acceleration died out and there are no new generations. We are not limiting the process, so we are just keep pulling until we want to, and when we stop, we are just canceling this flow, and it works fine. Now let's see how we are doing it. Which is limit. Actually, this is wrong. Actually, this is wrong. Because I limited to the number, not to the number of particles, but to the number, I set the limiting number of generation to limit, which is wrong because limit is huge number. This line is useless, actually. Or not. Sorry, I will just I see. It's my own function. Sorry, it's okay. It's not the standard limit function. It's my own limit function. It's okay. Now let's see how it works. What I want to do is to limit and produce those generation only until I hit the roof with those number of events generated. Now I go to this limit function and I see how it works. It transforms a flow into a flow. It actually does not change anything. What it does is it checks for each event for each generation passed to it. It checks if it is empty or if it is size too large. In case it is empty or size too large, it writes as the string and then return false, which means that we will not take any more events from this flow. It is terminated here. And if we need more events, then we pass this event and say that take more. So we do not do any actual running here. We only saying that there's a lazy function which generates events, then the lazy function which processes this flow and sets limits. And then we do two additional operations, like we want to show those events. For example, I want to show the plot of generation sizes, or depending on time, and I see here I take flow of generations and return flow of generation and use inbuilt on each function, which does not change the flow but applies this given lambda function to each generation which we receive. And in this I take this trace object, which is actually a plot trace defined here, and I modify it from inside this loop. Of course, I need to be careful not to do parallel access to external objects here, but since I know that all generations are evaluated sequentially, it's okay, but if not, I will have to place some kind of protection and mutex here. And then I want not only to plot the size of the generation, but also plot the distribution of events in the XZ plane. For that, I'm doing another function here. Again, it's just a processing flow. It does not change those results. It's just a pipeline, and what it does, it chooses a number of events, not more than these max particles, because we will have several millions of particles in the end, and we can't show them all. We're selecting a random 500 particles from them, not more than 500 particles, and then adding them to the scatter plot, also provided from external plot which we are modifying here. Not fully functional programming, but it's quite okay here. And then we are also adding additional delay here, because if we will see that if I won't add this delay, I think I can do it just to show you. I can move it from here and add additional step into this stream processing. Because if I do not do this delay, the simulation will end before we can see anything. Delay is also a suspended function. It means that when you are setting the delay, you do not consume a thread or processing resources. You just yield those resources to those who need it. And in this point, I actually start the simulation. Before this, nothing happens. When I start this, I say, now execute this pipeline in this coroutine scope. I won't go into detail what coroutine scope right now, but it is about the dispatching of threads, it's about error propagation, it's about all the machinery which makes the coroutine convenient. And then there is some additional lines about showing the plot with the traces with pre-generated. Here we use our brand new released Plotly-Kit library, which wraps Plotly and is quite convenient for such things. Now let me run it. Let's compile it, and in browser we see those generations and we see those XZ distribution, and the reactor actually explodes. Exponential growth, which means it exploded. And then it hit, when it will hit about million of events, you see it's getting a little bit slower because more events, it actually takes time to process them. For a small number of events, it's super fast, but for large number of events, it takes time to process them, and it finally hit the wall, and you can see the log that it's finished. The generation size is too large. Now we can cancel. We can cancel the server, and we can play around. For example, we can change. I'm not sure. We can change the size of the cloud. You see, still the growth, but it's much more smooth, and there is a chance that it will die out here. Probably won't at this point. No, it survived. But it's growing much slower. And probably we don't want to wait until it reaches its destination. So what we can do is terminate it right now. But it keeps simulation. I did not put a stopper here in order to stop the simulation when the web server stops, but we can do it. And we can probably even decrease it even more. And we will see that it will, you see it's some kind of slow decay, exponential decay and died out. Of course, if you have not a single bunch of 100 initial electrons, but additional influx of additional atmospheric electrons continuously, we will still have enhancement, which is Chilingarian called terrestrial gamma enhancement process, but no reactor explosion. That's all for the simulation. Please, if you have questions, just ask them. Okay, there will be a recording of this seminar, so you can think about it later. Additional important thing for our physicists is that in this case, since we are doing, we can inject transformation into our, let's see a code again. I will show you one important moment. Here, what I did is in this generate, I never changed how these new generations, I just produced them from the previous ones. But it is quite easy in this model to add an additional step which will transform the generation. For example, one of the theories about self-contained terrestrial gamma enhancement is that there are microdischarges in the cloud. When the density of electrons is too large, then there is a microdischarge and the actual local acceleration coefficient changes. It is quite easy to add this transformation here. You just need not to take the next generation as granted, but insert here generation transformation. You also can change the code here, so this transformation comes not from not hard coded here, but is taken the same way we are doing the explodes. So it's inserted somewhere here. It's what we should think about later, but it's provides us a lot of flexibility. Actually, when we are talking about Simba and about how it will work with the Bayesian tools, it will be the same way. In Simba, we want to, on each step, we want to analyze the probability of each particle, and in some cases, we want not to propagate particles depending on this probability. So we want to inject some transformation rules in this pipeline. It's exactly the same. Okay, final call for questions.
Yes, I just maybe have one question. Is so I'm not very familiar with coroutines in Kotlin, but is there some sort of dispatcher which helps you to sort of work out the number of tasks or jobs to allocate to different threads? Is this a good performance?
Yes, yes, it is. Here we have this, you see that we are entering this asynchronous context. And here I can explicitly say dispatchers default. The default dispatcher on the JVM, it is used by default anyway. It utilizes all cores, and actually underneath it uses Java work stealing pool. It's a very good performance. But actually you can tune it. You can use your own dispatcher. You can use your own thread priority mechanics. And in future, it will possibly will it will be possible probably to use dispatchers which automatically send automatically work on clusters, for example, that will send some tasks to be executed remotely without changing any code here. It's just for now, it's just very, very far future, and it's possible in the theory, but it's not implemented yet. But it will be at some moment. I believe that.
Okay, thank you.
Also, it is possible here to put some rules on error propagations, some logging, a lot of things could be done. Okay, no questions, so I will shut down the recording.